All right, so today's the last class on the caches chapter of this class. So announcements first, maybe before announcements, right? So let's do a quick discussion about PA5. How many are done with fully associative? Most. How many are done with direct mapped? Half. Okay. So as always, turn to Piazza. There's a lot of good questions and threads going on there. There's a few things I feel like I didn't emphasize enough, or just kind of neglected to kind of make clear what it is. So one is, what is the valid tag for? Right? So imagine when the computer starts up, or the computer is reset, everything is zeroed out, right? So in software, your software model of what the cache is, all the bits will be zeroed out. Right? Now suppose that you had either a load or a store or a modify that is looking for some memory that has tag equals 0. So it's going to look into the cache, and it's going to see that one of the lines has tag equals 0. It matches. So then what happens? Right, so that's jumping ahead, right? So exactly that's what you want to do. But if you had tag equals 0, and in one of your cache lines, tag starts up as 0 because the cache is cold, the computer just started, it's going to think, oh, this matches, so this must be the data, right? And of course, right now, the data is just a bunch of zeros. So that's obviously not good. It's a spurious, it's a false match. And so you need to have a separate bit that just keeps track of whether or not this cache line was actually even written to be correct, right? If it misses in tag 0, it loads in real data, A and B, for example, sets valid to 1. And so subsequent loads and stores that hit here sees that the valid is correct, or valid is 1, and then knows that, oh yeah, that's real data. Does that make sense? Make sense? Not clear? All right. So that's issue 1. Issue 2 is somewhat conceptual. So what is this cache? We're talking about this cache. Where does cache exist? Like where do you find cache? It's in the hardware, right? It's in the CPU, right? So the CPU memory cache, it's made of transistors. It's physically hardware, right? What we're doing here for this programming assignment is we're writing a simulator for hardware. Right? So this cache is not some software construct that actually exists in your computer as software or as memory, but instead is hardware. We're writing a program to simulate the behavior of a cache. Right? The cache doesn't live on the stack. It doesn't live on the heap. It's physically hardware on the CPU. And then the third kind of issue was about distinction between load, store, and modify. Right? So L stands for load, S stands for store, M stands for modify. And all of these operations, they come from the assembly code. Valgrind, when it's generating the memory trace, is looking at the assembly code and seeing whenever there's some kind of move Q, some kind of move operation between the CPU and the memory, then it marks it down as a load, a store, or a modify. So load means loading data from memory. Store means storing data from CPU to memory. And all of this is mediated through the cache. Right, so kind of a tricky thing is, as it turns out, for the purposes of this programming assignment, you don't really have to care if it's a load or a store. They're effectively the same because we're not actually modeling the data, right? We're just saying which caches are occupied by which tags. And so for the simulator that you're writing, loads and stores are effectively the same. And then the modify is a load followed by a store. Those two axes. Okay, so that's just to kind of clarify some things that might have gotten lost in the explanation, right? So the lecture on Tuesday was really about appreciating the difference between fully associative and direct map caches and why set associativity is nice. And these are kind of some of the more like unspoken things I didn't really fully mention. So any other questions about those first three parts of the programming assignment? Okay, last chance for these logistical questions. Okay, so yeah. Okay. Yeah, so let's take a few minutes to work through an example for that. I'm looking for this. Okay, so let's study set associative load stores a little bit more. Right, so here's the work example that we had from Tuesday again. We're going to focus on set associative, the last piece that we did in the last 10, 15 minutes or so. And the reason we have to pick a specific example is because each of the examples, each of the different designs, they have different choices for how many bits are allocated for the block offset, the set index, and the rest of the tag. Right, so we will do a operation, we'll say load, and let's just say that we're doing column traversal, going downward through the array. So we'll do load 0x100, right? And this is a binary number, so 0b 0001 0000 0000. It's a 12-bit number here. And the question is about how do you figure out which set and which way this cache miss should go into. So the first thing that we always do is figure out, well, which bits belong to what, right? And all of these examples on the Excel spreadsheet here, which is different from what's in the programming assignment. These examples here, we choose B is 3 bits. Block offset, so B equals 3, B equals 8 byte block offset. And so in the cache, we had, this is now a, how many set cache? This is a 2 set cache. One. Right, 2 set cache because we chose little s to be 1. And each of them we allocate 2 ways. So there's 2 tags in here. Each of them holds 8 bytes. Any quick questions about how we got to this point, right? Just based on the parameters alone, how we figured out this is the design of the cache. Right, so big S is 2 sets. Big B is 8 bytes in each block. So every time we load something from the memory, it will always grab 8 bytes at once. And within each set, we have 2 ways. Right, so this is a set associative cache that has properties of both fully associative and direct map caches. Okay, so now the question is back to, yeah. Yeah, so so we chose the example where little b is 3. This could be different, right? So we could say little b is 4, like in the programming assignment. If little b is 4, that means that each block is 2 to the power of 4, which is 16 bytes at once. And what that would look like here is each block is even longer, right? So it will grab 16 bytes at once. 16 bytes would be good for grabbing 4 ints, 2 longs, and so forth, right? Is there a specific reason why E ways needs to be 2? No, there's no specific reason, right? We're choosing for this example. And again, right, these parameters are tuned so that we can appreciate the difference between these 3 designs. But E could be anything else. Little b could be something else. Little f can be something else. Okay, so what we're going to do now is we're going to perform this operation and see how we figure out where inside the cache it goes. So the set index is 1 bit. So this is set 0. We know that it's going to, wherever it's going to be stored into the cache, it will be in set 0. And the tag is all the rest of the bits. So all the rest of the bits, these are 12 bits of tag. Tag here effectively is 1, 2, 4, 8, 16. So when we load 0x100, we come to set 0, see that, well, neither of these cache lines are valid. And so it's a cache miss. It's a load miss specifically. So we pick one of these ways. We store tag as 16, and we pull in A and B. Right, so that's how we figure out which set it goes into. Let's do one more instruction and see how it picks which way it goes into. So let's, as we said, we're doing a column order traversal right now. So the next instruction is load 0x120. This address is 0010. The tag is now 18. We come in, we load 0x120. Again, we see S, this is 0. So this is the set 0 here. We know we're constrained to looking into these 2 buckets now, this bucket here, these 2 lines. It looks across these, he sees, okay, this one's valid, but its tag is 16, which does not match 18. So that's not it. Looks over here, this one's empty. This one's not valid. So this is a load miss. Load miss, it pulls it into the cache, just in case it may be useful in the future. Writes down tag is 18, and it gets IJ. Right, so that's basically how you use the set and whatever space you have in the cache ways to figure out where a cache miss should go into. Yeah. Yeah, right. So this question about, since you're asking about that right now, let's talk about that. And in fact, I'll have to pull up Tuesday slides. Right, so these questions are about writing policy. Is here. Right, I talked about how all of this is dealing with is going between CPU and memory. Loads go from memory to CPU. Stores go from CPU to memory. And there is kind of like a synonym going on where loads, we can also call them reads. And stores, we also call them writes. So the question of what happens when you write from CPU to memory, what's the policy surrounding that? This is called write policy. So again, all of this is mediated through the cache. And this is kind of a subtle choice, right? So this slide here, what you see on the projector right now, is all the choices, some of the choices for write policy. And again, the way we organize is we can think of this as, well, there's hits and misses, right? So there were there were load hits, load misses, and now we have store hits, store misses. So these are a little bit more tricky, right? Store hits, store misses, aka write hits, write misses. How do we deal with them? Right, so if it's a write hit, easy, right? So you are writing from CPU to memory. You see that there is a cache line there. And so the decision now is, okay, so clearly if the cache line exists for this store, well, the CPU should update the cache. The question now is like, should that update the memory? Right? Do you have this additional traffic from the cache back to the memory? And the simple thing is, well, it should also be consistent, right? So the memory should always be consistent with the cache. So you update the cache and you update the memory. That's called write through. And that's simple. But there's a different policy here called write back, which is more complicated. And it's useful if you have a bunch of CPUs, right? So right now, you know, these real CPUs now are 16 8-core, 24-core CPUs. And so every CPU has its cache, and they're all trying to talk to the memory. And so one design in very advanced, more advanced like parallel processors is you could do a write back policy highlighted there, which is if a CPU is writing to memory, there's a write hit, meaning it sees that, oh, it already is my cache. It updates the cache, sets a dirty bit, and then fails to automatically write it back to the memory. It saves that step. Right? So it kind of works with its little scratch pad of what to write. And then later on, some other events will trigger a full write back. This has nothing to do with the programming assignment that we're doing, right? This is an advanced topic. Again, right, so we talked about write hit. You're writing from CPU to memory. It sees it in the cache, what to do. Now we talk about write misses, right? So CPU store to memory, CPU storing to memory, writing to memory. It doesn't see it in the cache, right? It's a write miss. So what's the policy there? Again, there's two choices. One is called write no allocate, which is you're writing from CPU to memory. On the way, it sees that my cache doesn't have a local copy of it. So that's fine. You just go write it to the memory, and this cache doesn't pull in that line. This is called write no allocate. And in that case, writes and reads will be very different, right? Reads always bring it into the cache, writes skip the cache. The other policy is called write allocate, which is actually more complicated in terms of hardware, where if you're writing from CPU to memory, on the way, it doesn't see it in the cache, leading to a write miss, then it triggers a pull from the memory into the cache so that you have a local copy. This is called write allocate. So we can compare this to the assignment description now, right? So for the assignment description, all three cache designs that you're asked to simulate, they are all write back, write allocate. All three parts are write back, write allocate, write back, write allocate. Here, write back, write allocate. So it's write back, write allocate, which in terms of hardware is more complicated, but as far as software goes, it's actually the more elegant kind of thing to simulate, to model. Right? It's because I gave you these choices of write back, write allocate, that basically loads and stores are identical. You don't have to treat them separately. Okay, so that's this slightly advanced topic here. So what I want to also emphasize is cache replacement policy, right? So there's several questions. There's like a taxonomy. If you check the textbook, there's like a taxonomy of questions to ask relating to cache design. They are cache placement, cache replacement, write policy, and then kind of the hierarchy. So this is an additional kind of question. This is relating to FIFO versus LRU. So first, let's talk about the trivial case. Right? The trivial case here is the direct map cache, which is every address that you write and read to and from, the set index dictates exactly which set it looks into, and each set has exactly one way. Right? So if it's already occupied, then it's immediately an eviction. And in these cases, there's no such thing as a replacement policy. Right? The address, the set index in the address fully dictates where in the cache it goes to. So for direct map caches, there is no replacement policy. Things get more interesting when we talk about associative caches, right? So either set associative or fully associative. Here in these cases, essentially when you're figuring out where inside the cache it goes, the set index narrows down the choices, but then from there, you still have multiple ways to pick from, right? So here, this is an E equals 2 two-way. So there's a decision to be made of, well, where does this go, right? And this is called the replacement policy. If it's full, then you have to pick one to pick on and evict that to make space for the miss that you're trying to pull in. So the replacement policy here, there's two sensible things to do. Right? The simple one is called FIFO. The picture is here. Right? So correlating that to the slide here, the address tells you, well, the address doesn't tell you exactly where inside a cache set it should go to. Within there, you have capital E ways to figure out where to place it in the cache. And that decision, there's two choices, FIFO or LRU, simple choices. One is FIFO, right? So FIFO is basically, it's like a queue, right? So you look at both of these lines, whichever is older, whichever came in first, that's the one to eliminate, right? So in our example, A and B came in first. And so when this is full, eventually A and B will go first, and then later replace I and J, and so forth. That's called FIFO. There's a different policy, which is more complicated to implement, but more sensible, right? So the LRU policy, least recently used policy, basically says, well, sometimes you have some data that's old, but still being actively used, right? And if that data is being actively used, then it should not be eliminated. So every cache line has a little counter associated to it to keep track of how recently it's been used. And the one that has least recently been used is the one that gets evicted. Yeah. Sure, right? So how do you implement this? Well, there's many ways you can implement this. If you were building it as a queue, okay, so I'll pull up this slide again and look at these boxes here, right? If you were implementing your cache model as like a queue, well, one way you could go about it, among many other ways, Right? There's many, many ways you can implement this. And I'm not even advocating for this way of going about it, but it helps you think about what's the approach, right? So you have the cache set, let's say set 0. It's now like queue. Suppose that you have 4 ways here, and you have a queue, and so once it's full, then you dequeue the top and then push back. This is FIFO, right? You're using a queue to model the FIFO policy. Or if it's LRU, well, what does LRU look like? Well, maybe one way you could do it is if you hit this block, for example, right? If you hit this block, automatically this becomes the most popular and important one. It's the most recently used one. So it should get moved to the back. So you take this cache way data and you put it back to the tail of the queue so that it's last in line to be evicted next. Right, so that's one way to go about it. Again, many ways to go about it, but this is to illustrate what that might look like as far as logic goes. Yeah, you had a question? So I don't even really remember what's in the provided code, right? So you're talking about like how do you correlate this to the provided code? Again, the provided code is just one particular approach to go about it. You could ignore the provided code, or you could follow the hints of the provided code. Either is possible. Good. Anything else here? Okay, so before we depart this topic, let me just transition over by kind of having this final kind of wrap up brain teaser. Okay, so we talked about how the capacity of a cache is calculated by capital S, the number of sets, capital E, the number of ways, and capital B, the size of the block. Okay, so here the picture here is, well, capital B is the size of the block, capital S is how many sets there are, and capital E is how many ways there are in each set. So with that in mind, what is it that's providing spatial locality support? What is spatial locality supported? Yeah, Donald. Yeah, so spatial locality is if you have array item A, array item B, which is next to it spatially, might be useful next. And so in other words, spatial locality is essentially supported by the size of the block. Right? So if you have bigger blocks, if you can like pull in 16 ints or 4 ints, then your support for spatial locality is even better. Right? You just grab A and then B, C, D, E, F, G all come along with it. That's spatial support for spatial locality. What's temporal locality? Sort of. Can refine what that is. So what's temporal locality in context of our array problem, right? First of all, which one had better temporal locality? The row traversal or the column traversal? So row traversal has good spatial locality, right? So you're reading A followed by B followed by C. In terms of temporal locality, the way to think about this is you can pull in A, B at once, right? The block size provides pulling in 2 integers at once. A, B comes in together. IJ comes in next if you're doing column traversal. IJ comes in together. So you actually wait a cycle before you use B. Right? So the spatial locality supports A and B coming in together. And the question now is, well, is B automatically used next? And in the column traversal, while B is not immediately used, you wait until I and then followed by B. So the temporal locality wise, row traversal is still better, and column traversal has slightly worse temporal locality. And what's ultimately supporting temporal locality inside the cache design is the number of ways. Right? You can think about this ways as kind of a buffer, right? A kind of buffer in that once something is missed, it gets pulled in, AB gets pulled in, B is not immediately used, but we just add it to kind of, as we say, a queue, right? So later on, it may be useful again. So ultimately, it's this number of ways that's providing support for temporal locality. It acts as a kind of a buffer such that data that's not automatically immediately used could be easily accessed later on. Right, and then, so basically what I'm getting at is here, spatial locality supported by B, notation, answer, B. And temporal locality supported by B. Okay. Very good. So now let's go on and talk about, we talked about how the hardware properties of the cache, it has these peculiar choices. We're modeling the hardware properties. So now the question is, how do you write code that runs well on caches? Could you do things as a programmer to make a difference? Right, so there's certainly many approaches to this. Oh, I'm getting lost in my slides here. Okay, there's many approaches to go about this. So the essential idea is you need to write your code to improve spatial and temporal locality. That in turn leads to its behavior in the cache that maximizes the hit rate. Oftentimes data is found in the cache, high hit rate, and you incur few misses and few evictions. Right? Remember, the things that cost the most time are these misses and evictions. Access to the cache is cheap and fast. Access to the memory is slow. There are some things that you can do as a programmer to improve your locality, and there are things that the compiler can do for you to improve locality. Right? So let's study 3 different examples here. Right? So the 3 examples that we'll talk about here are loop interchange, cache blocking or loop blocking, and the last one is cache-friendly, cache-oblivious algorithms. Okay, so loop interchange. All right, so let's go to a code demo now. All right, so in the programming assignment 5 directory now, there should be an example called cache-friendly, and inside there, I have a program called matmul. And let's study what's inside matmul. Okay, so inside matmul, there's a matmul routine. Okay, so this is basically, you have matrix A, matrix B, and matrix C is going to be C equals A times B. It also takes as parameters the sizes of the matrices. Okay, so I should illustrate this. So A is going to be dimensions mn. Oh, I'm not sure actually this is important right now. So let's ignore the dimensions for now. Right, let's focus instead on how this matmul is taking place. Okay, so I have 3 versions of matmul here now. One is called matmul ijk, another is called matmul kij, and And the third is called mapmul JKI. Okay. And the key thing is these mapmul routines are written so that you have these loops, right? Mapmul, naive mapmul is a n to the third power n cubed algorithm. And the naive way is to write it so that you iterate over I, iterate over j, and iterate over k last. And you find the elements of C, the product matrix. The other couple versions of mapmul are basically the same idea, but we permute the way that we nest the loops, right? So here, we iterate over k first, and then I, and then j. And then the third way is we iterate over j, and then k, and then I, right? Functionally, should be this, are these any different in terms of the computed results? Want to take a guess? The computed result should be the same, right? The computational results, like what they find C is ultimately going to be. The way they go about it is different. And so what's your predictions on whether or not this has impact on anything in the real world? Right? Curious, right? So we go to the main method. The main method basically tests all three of these functions, right? So we set up the data. We have matrix A. It assigns to matrix A some random data. It sets up matrix B. It assigns to matrix B some random data. Again, we time code, right? So we're going to time matrix multiplication via IJK, the first nesting. First of all, it prepares the matrix C to hold the results, right? Now it's some memory of the right dimensions to hold the matrix multiplication result. Start the timer with the clock, end the timer with the clock, and in between the start and an end, we time the time it takes to perform mapmul IJK, which multiplies matrix A and matrix B, and stores it in matrix C, which here we call IJK results. And then after doing the multiplication and timing it, it just prints out the time it took to do the computation. We repeat this 3 times, each time for different versions. So next we do the KIJ version, and then finally the JKI version. We then double check that the computational results are all the same, right? We check all 3 versions, all 3 of the calculated C matrices from the different versions, assert that the calculated results are all the same, and then we just clean up, right? And the key thing we want to observe is the time it takes to do all of this. Before I run this code, any questions about what we're doing here? Let's run the code. So we'll double check the makefile again too. So for the compilation, I want to make sure we're doing O0, no optimizations. And we'll compile and we'll run it. And while that runs, let me just emphasize that these are huge matrices, right? So I'm multiplying 1,000 by 1,000 matrices. So matrices A, B, and C, they all have 1 million elements each. So we see there's actually a timing difference, right? So IJK finished, KIJ finished, and wow, JKI is much slower, right? And we can do the same thing as we did before, which is to double check the order in which we do things. Does that matter? And it doesn't matter much here. These matrices are so huge that the who comes first matters much less now, right? So why is it that there's this huge difference? Why is it that the KIJ version is the fastest? Anyone want to take a guess? Yeah, guess back there. Yeah, it's all the differences in the Ki and J, and what does that influence? Right. the number of times the loop been run, right? How many total multiplications take place in each of these? The total number of multiplication operations is all the same. Right? The dimensions of the matrices are all the same. It has to do the same amount of work, ultimately. But the order in which it goes through the matrices is different. Okay, so what does that impact? Well, what that impacts is what we're talking about here, right? The way you write the program has implications on the spatial and temporal locality of the program, which will influence what the cache hit rate, miss rate, and eviction rate is going to be, which then affect how quickly the program runs. So let's see. Okay, so yeah, let's go to the textbook slides now. And so this is the textbook slides. I'm using this section on rearranging loops to improve spatial locality. And here they walk through what I just explained, which is we're doing multiplying matrices size n times n. It's a total of n cube operations. For whatever you do, it's going to be an n cube number of multiplications. And here it explains what I, j, and k each are supposed to do. Right, so the convention that they use is ij is always the row and column indices of C. A is always indexed by I and K, and this K is special, right? This is the row, this is what we have that in our mental picture, right? K is this iteration here. Right? If this were A, let me write this down. A, B equals C, multiply. The way you do matrix multiplication is this element here is the sum of these multiplications. Notice how I'm going through the columns of A while going through the rows of B. Make sense? Right, so that's the K indexing through that operation there, the columns of A and the rows of B. So now we next also review how these matrices are stored in the memory. Right? So our memory is really just one long array. Right? It's just one long array, and all of these matrices, 2D arrays, are really just stored as in row 0 of A, followed by row 1 of A, followed by row 2 of A, followed by row 0 of B, followed by row 1 of B, and so forth. Right? They're laid out in memory as just one long linear array. So this means that if you were iterating through A in a row-wise traversal, well, it's very natural, right? You just go through the matrix linearly, and that'll be a row-by-row traversal of A. But if you go through A column by column, if you go through A column-wise traversal, you skip rows instead, going down the array, then it's like it jumps around. Right? You go from the first element to the first element of the second row to the first element of the third row, and you come back and you jump around and jump around. Makes sense, right? So ultimately, this problem is very similar to our row and column traversal that we've been studying for some array, right? And what's the difference here? What's the kind of what's the part that we're going to trip over here? Right? It seems like we already talked about this. The sum array rows and sum array columns, we seem to already have been dealing with this. So what's the key tricky thing that's going to be slightly different here? Yeah.
Is that the
is it because the cache is going to wipe what we want in the multiplication? That's kind of the ultimate symptom, but that's true. But what I was trying to get at is we have three matrices going on here. Right? Before we were just doing sum array rows, sum array columns. You had one matrix. Here we have three matrices, and there's no single way to traverse all three of them in the natural way, which is row by row. Right? Either you go through A in the natural way, which then forces you to go through B unnaturally, and so forth. Or you could go through A in the natural way, or sorry, you go through A the unnatural way in exchange for going through B naturally. Right? You can't go through all of them the natural way, which is to go through them the whole row at a time. Okay. So the next series of slides is, there's going to be 6 slides here in the textbook slides. 6 sets of slides, 6 slides, and they're basically 3 groups of 2. Okay, so the first group is this IJK group. The second set is this KIJ group, and the third set is this JKI group. And as it turns out, each of these pairs are going to be pretty much the same. So we study the naive way, right? The IJK approach. And what they point out is what you have to focus is this innermost loop, right? So what goes on in the innermost loop? What are the multiplications taking place immediately after each other in time? And what's happening in the IJK approach is you go through A, row-wise, or you go through A, you have the same row, go through column by column. And then for B, it's going to be a column order traversal, right? So for B, you pick one column and you go down the column, each time hitting a different row, right? So the A traversal will be very natural, and the B traversal will be unnatural. And so you can see you can observe in the kind of the metrics of this traversal here, A misses sometimes, B misses all the time. Right? B will never be in the cache properly because these rows are so long that B's contents are never being stored in the cache. Right? Any questions up to here before we change the traversal direction? Yeah. Why is that B is never in the cache? Right? So how are we traversing through B right now? And we're doing the IJK version, which is we go through A, row order, we're going through B, column order, in order to calculate this element of C. And the key thing is this B, right? Matrix B is stored in the cache, so it's stored in the memory, row by row. So this is going to be row 0 of B, row 1 of B, row 2 of B, row 3 of B. And because we're going through it downward, the way that we're accessing B is going to be like this. That part makes sense? And why is it that this doesn't work well in the cache? And we're going to actually appeal to what we did in the exercises before, right? So we already experienced how sum array rows and sum array columns always has more trouble trying to work well with the cache, right? So on that alone, I can already assert that this is not as good, is not as cache friendly for B. Right? We saw that, which is in our spreadsheet here, the sum array columns approach, sometimes it just never works well with the cache, just like this case here. Column approach you're trying to skip around in the memory so much that the cache cannot cache it. Good question. The key word I'll say here is this traversal B does not have spatial locality. The accesses are not adjacent to each other, right? So here you get this element from row B, and the cache will be helpful. It'll get you this row, but that's not what you need next. What you need next is some other line altogether. And so the spatial locality support is not helping you out. Okay, so that's approach one, right? IJK. And I'll go now to KIJ, which is the best approach, right? So in this approach here, the key thing is we now go through B and C, both of them in the natural row order, row-wise traversal, right? So it holds A constant. Right? So we grab hold of some element in A. Grab hold of some element of A, we record it as R. And then once we have that R ready at hand, we then go through all elements of B and C that interact with that one element of A. Right? So we multiplied this with this element to get a component of C here. We take A multiplied by the second component of B here to record this element of C, and you traverse through C. Same thing, row order traversal. And you're not finding the whole value of C at that one time, right? You're just accumulating the products until ultimately at the end of the whole loop, you find the full value of C. Right, so here, the traversal is very natural for both B and C. And so you can look at the metrics here, which is for this innermost loop, your traversals of B and C, they're going to miss sometimes, but there's not a single case where they miss all the time. Like compare 1/4 miss rate versus here, B was never being cached. So this is the best one. We can go and look at our computational results here. So IJK, first one was fine. KIJ, where J is the last index, is the fastest. So this confirms here. So now let's look at, well, why is the last one, right? The third approach, why is that so slow, JKI? So JKI is the worst. Right? JKI, you're going against the grain for both matrices A and C. You hold some element of B constant, grab hold of that multiplier, and you're traversing through A and B downward against the grain for both. Yeah. Right. Right. All right. So think about, so let's go back to the good approach, right? So think about what's going on here. I grab hold of A as a multiplier, and while this is on hand, we're going to calculate this element of C, its component. And since we already loaded in this whole row doing that, and we loaded in this whole row for C for doing that, well, may as well go through all the work that's relevant at the same time. Right? It's already on hand. It's local now. So do the work while it's ready in cache. Strike the iron while it's hot or something like that. You know? That's the idea. And this last one is the worst, right? So this one, all the loops, the innermost loop iteration is constantly jumping around in the memory locations. And so for A and C, there's cache misses on every iteration. Yeah. Right. So again, yeah, so same idea, right? So the picture here is if you're going through matrices row at a time, a whole row at a time, you're just going through it in memory like that, very naturally. But if you're going it through columns at a time, then you're jumping around in the memory. Great. Yeah. Yeah, so we can study what's going on here, right? So let me do the explanation again before the JKI one. What do I mean by holding an element fixed? So for that, let me just use concrete dimensions. Let me just make A, B, and C all be 2 by 2 matrices. Right? So we know that matrix multiplication is that C00 equals A00 times B00 plus A01 times B10. Make sense? And so our natural way that we learn how to do matrix multiplication is to go through C this way. Right? We go through whole rows of A, whole columns of B, whole rows of A, whole columns of B to do the computation. That's the natural way. That's the IJK approach. Right? And so here, JKI kind of has to force us to go against our natural way of doing the way we learned it usually, right? The JKI approach here, what it does, it holds B steady, right? So I have this element R equals B00. Well, who cares about B00? B00 is important for calculating C00 equals A00, B00 plus something. I don't know what the other part is. So we'll do that computation. And who else also cares about B00? Well, B00 is also used in C01 equals B00, A, that's that one, which is that one, yeah, still. Plus something else. Right, so we pick up B00, we have this in the second to outermost loop here. We grab hold of that. And then while we have B00 ready at hand, we use it to update all of the elements of C that want to see B00, which would mean that take B00 multiplied by this one, add it to the accumulation here. Also do A01 times B00, accumulate that to C01. Yeah. Oops, yeah. Good point. So I goofed here. What I wanted was C10 equals A10. Yeah. Same idea. Again, this requires us to do some mental gymnastics, right? So B00 is used here and here, and to compute this one and this one, it's multiplied against A00 and A10. So that's what this picture is saying. we pick up B, and holding that fixed, all the elements of C that should accumulate B00 in some way are all of these elements in this column of A, which will result in the elements of the column of C here. Okay. So the next takeaway now, right? So does this mean that we should go back and rewrite all our matrix multiplies, right? This is a shocking revelation, right? We've been writing our matrix multiplies, almost certainly everybody's writing it the IJK way, right? Does this somehow mean that we have to unlearn how we write matrix multiplies? Well, fortunately, you can use the compiler for that, right? So let's go to the manual for GCC. And as it turns out, the GCC compiler can do some of this optimization for you, right? So this is called loop interchange. And the manual for GCC will tell you loop interchange what am I looking for? A loop nest. Oops, okay, so I can't find exactly where it is, but the manual documentation for loop interchange will tell you that it will automatically do this conversion from IJK to the KIJ version. Okay, so you can invoke this compiler flag. We go to our make file again. And instead of doing O0, we tell it, okay, invoke loop interchange. And let's see how well it works, right? So ideally, you would want to see it that it's then able to optimize them to take better amounts of time. And as it turns out, it seems to not work that well, right? So this is kind of a tricky thing, right? So these optimizations, you hope that they would do these like reorganizing the loops for you. But as it turns out, sometimes the compiler can do it for you, sometimes it can't. Sometimes different combinations work well with each other, sometimes they don't. And who knows how exactly this compiler was compiled and configured. And so what you try to do is, well, let's just crank up the optimization levels, right? So you could give it O1, which is a whole set of different types of optimizations. And from there, it's able to decrease the time, right? So here, O1, it worked well for IJK, it worked well for KIJ, but it seems like it doesn't work really well for JKI. Right? So we keep cranking up the optimization levels. So O2 now, right? O2 is another set of optimizations that GCC will try to invoke. And O2 doesn't work on JKI still. So O3. Still doesn't work for KIJ very well, JKI for very well. Right, so what's the takeaway here? Well, the takeaway is kind of unsatisfying, right? The takeaway here is these choices that you make as the programmer, writing IJK versus KIJ or JKI, they still have implications on the performance of your program, and they have implications on how well your compiler can tackle those programs. So notice how here, if you wrote it in the IJK approach, the compiler does a fairly good job of decreasing the time. And if you force it to go about the bad way, well, the compiler can't really help you much. There's one kind of intervening thing here too, which is the -G flag, which is for debugging records. That also does kind of mess with the optimizations a little bit. Okay, so let's try that again. So let's do loop nest optimize. Try that again. So again, this is multiplying 1,000 by 1,000 matrices, 1,000,000 elements each. And the loop nest optimize. Yeah, anyway, we'll let that run. Okay. Oops. So that was one approach to writing cache-friendly code. What's another approach? So the second approach here is called cache blocking. So cache blocking, the idea is, we'll go to the textbook slides again. All right, the idea here is you will help the compiler by increasing spatial locality. So cache blocking is this idea where here's our default matrix multiplication as before, where we're striding across the whole matrix at once. Cache blocking is this idea where instead of going across the whole matrix, we focus on some subset of the matrix at once. Right? So instead of striding across the entire matrix in this loop here, instead you divide and conquer. Right? You have a separate set of outer loops here, where you make it so that the loop indices inside the inner loops, they don't increment across the whole matrix at once. So the idea here is you focus on calculating this submatrix of C, which would be the summation of this submatrix of A times this submatrix of B times this submatrix of A and this submatrix of B, so that even for B, right? So for B, you have to traverse through it against the grain. Well, here, because you're only looking at a submatrix of it at once, the locality is still improved. Right? So you're shrinking the problem so that effectively the innermost loops, they don't see the whole height of the B matrix all at once. So this is going to be kind of an approach that you'll experiment with in the 5th part of the programming assignment, cache blocking. Anything I can say here to kind of illustrate this better? So what does this really do, right? So what does this really do? Okay, so in this version here, we're going back to the IJK approach again, right? So if you look at the innermost loops here, this is IJK, which is the natural way of doing matrix multiplication we're used to, which is you go across the rows of A and then down in the same column of B, down a single column of B. And we've established that the reason why the performance of this is slow is because as you go across these long lengths of B, the elements of B are always flushed out of cache. Right? So B, let me draw that in detail here. So let's focus on what goes on in B right now. B. Okay, so what happens now is the reason why going all the way down B is inefficient is because suppose you got this element of B, the caching system, the cache hierarchy will give you, as spatial locality goes, these elements in B, right? But then you don't actually use any of these, and instead you annoy it and you get this element, which the cache hierarchy, the spatial locality will give you these elements of B, right? The whole block. And so by the time you go all the way down B and come back up again, and you wanted this second element at the top, well, that's long dead, right? That's been long evicted a long time ago. So instead of going all the way down, what if we do a different approach, right? We go through the elements of B, kind of across a smaller subarray of it, submatrix of it. Right, so in this approach here, you get this element of B. The cache block will give you this whole row. And the next thing you do is, well, you're going down B. So you don't immediately use it. So you get this element. It gives you, the block will give you this whole row of B. And by the time you get to the bottom, here, instead of going all the way down B, you come back up and use the data while it's still fresh in the cache. Right? So by shrinking the size of the sub matrix of B that you're using at any given moment, you try to use the data just before it gets evicted. Right? So this is the cache blocking idea. Okay, so you'll give this a try in the 5th part of programming Zone 5. Yeah. All right, so the question is like, how big should you set this parameter, right? There's this parameter here called capital B, which is a block size. And well, the answer is you kind of just experiment, right? Because there's actually multiple, you see how there's like all of these loops in here, right? You can check the notes, what it says as far as kind of analytically, what's the optimal block size. But as far as kind of the programming assignment part, this is cache blocking. Actually, it's part 4. As far as that part goes, you can experiment with different sizes of the blocks and see which one gives you the best cache performance. Does it grab from memory the adjacent blocks that would be there? Right, so the cache blocks always get rows. Right, so if you wanted B00 here, then it'll give you B01 for free. Right, and the trick here that you're pulling off is before that row gets evicted from the cache, you go back up again and reuse B just before it's evicted. This improves the spatial locality. Okay. Oh, let's see. The thing what we'll do is this, right? So in 5 minutes, I'll try to explain what the last component is, but then I'll kind of assess if I've given enough information to explain how this works. Right, so we talked about how there's 3 approaches to improve cache performance. One is loop interchange, right? Rearranging loops so that it matches the direction of the memory traversal. The second is cache blocking, where you're shrinking the problem so that you see small enough subproblems to fit in the cache at any given moment. And this last one here is going to be called cache oblivious algorithms. And the motivation for this is, well, in the real world, caches are a whole hierarchy, right? So there's L1 cache, a small cache, which is backed up by a bigger cache called L2 cache, which is then backed up by even bigger caches called L3 caches, and maybe even more. And finally, it connects to the main memory. Right? So it's like a Matryoshka doll. You know, the small caches nest inside bigger caches, which are then wrapped around by the main memory. And you can look at the real world data, right? You look at real designs for Intel CPUs. Right? This is the real design parameters for an Intel 2020 CPU. And you see that has 3 layers of cache. Each one gets bigger and bigger, and they get bigger and bigger and more complex, and the access is slower and slower. Right, so the idea here now is, well, how do you write programs to target something like that? Right, to write programs that target that, you kind of want a different strategy where you don't have all these parameters to tune. Right? So here you had all these parameters, which was, well, there's this block size that you have to guess, right? And you can experiment to figure out what's the right block size. What if instead you had kind of a different approach where you take any problem that you want to do and you kind of recursively shrink the problem smaller and smaller until it's the right size to fit in a particular cache. Right, so here in this abstract picture here, the idea here is, well, for the smallest innermost caches, the L1 cache, maybe it's able to help you cache all the data needed for this tiny subproblem here. And then for the L2 cache, the slightly bigger cache, that helps you take care of a bigger problem. You can cache all the data in here, right? And then the L3 cache, they can help you cache all the data you need for this big problem here. Right, so in the 5th part, the actual last part of programming assignment 5, the idea is to experiment with these divide and conquer approaches. Where you take a big problem, you decompose it until it's small enough to fit in each different layers of the cache. Okay, so with that, I think let me just give one more kind of final motivation for what this is about. So the cache oblivious part of the assignment is, the task is to transpose a matrix. Okay, so you're given matrix A, you're given matrix B, and matrix B is supposed to be the transpose of A. Right? So what is the transpose? Well, the transpose is basically you mirror image a matrix over its diagonal. Okay, so A00 becomes B00, A01 becomes B10. Okay, so the kind of tricky thing about the matrix transpose task is, once again, suppose B equals A transpose. If you're going through A naturally, row by row with the grain, you're forced to go through B against the grain. If you're going through B with the grain, you're forced to go through A against the grain, right? So there's no way to satisfy both here. And the idea is that you would use a divide and conquer approach, where you have this matrix A here, and instead of going to transpose the entirety of matrix A at a time, you transpose submatrices at a time. Right? So you would transpose this submatrix, followed by this submatrix, followed by this submatrix, and this one here. Right? So this is a general hint for the cache oblivious part of the assignment. Okay, All right, so I'll stick around for questions, but otherwise, good luck. See you next week. Hi.